Welcome back. In this lecture, we will address two issues. One is on electrostatic principles. The other issue is on Faraday's law. What I have found in my practice of electrochemical systems, analysis of electrochemical system, is to have a good intuition on electrostatics. Many concepts that we utilize in electrochemistry can be interpreted from the standpoint of electrostatics. These are principles that you would have learned in your high school, but you may not have used it recently, so it's good to go and brush up your electrostatic background. So I'm going to just emphasize that we're not going to go deep into these things. It is just that you have to go and revise your electrostatics from high school. In the last lecture, we gave an introduction to what we are going to cover in this class. The context for this course is on energy applications and chemical applications, chemical production and so on. So while this may seem rather narrow, the scope of electrochemistry is much wider. Electrochemical systems play a big role in a lot of semiconductor processing and so on. So we will, along the course, we will address these applications also. Chemicals, entire metabolism in human body is a matter of chemical production and chemical balance. Okay, so electrochemistry plays a central role in these systems. Although we will not address the electrochemistry, bioelectrochemistry, or the electrochemistry of biological systems, it is important to realize that electrochemistry plays a big role in such systems also. We will do a lot of analysis. We will, by that, what I mean is that we will look at the underlying equations in thermodynamics, transport phenomena, and electrochemical kinetics. We will have how to frame these equations, how do you interpret this equation, how do you set up this equation in the context of electrochemical systems. That's what I mean by analysis. And synthesis is how do you use these equations to design electrochemical products, batteries and electrochemical product, and so on. Okay, so we will do both these things in this course. We introduce the notion of an electrochemical cell, a rather elementary introduction, mainly pointing out the components that are present in electrochemical cell. We also differentiated two types of electrochemical cell. One is the galvanic cell, where an exothermic reaction is utilized to generate electrical work. Another is the electrolytic cell, where you impose an external potential and run an endothermic reaction. In all these things, how you may affect the energy of the electron, okay, plays a big role. Okay, so there are thermal reactions. So electrochemical reactions are very different from thermal reactions, okay, because the coupling between energy of electron and potential is very different from the way you think about thermal reactions. So that plays a crucial role that helps in understanding why electrochemical cells are not limited by Carnot efficiency and so on. Okay, so we'll get into these topics gradually as we progress in this course. So we looked at lead acid battery. This is almost everybody must have seen a lead acid battery. You should now get a better appreciation what is inside a lead acid battery and how it may act both as a galvanic cell and as an electrolytic cell. When the battery is discharging, the potential which the battery provides is less than 2 volts. Let's say ideally, let's say you're able to get, let's say 1.5 9 volts. In this mode, the lead acid battery is acting as a galvanic cell. So when the battery is discharged, it can also be charged by imposing an external potential. Under those conditions, it acts as an electrolytic cell. Okay, so, and we also introduce certain jargons which you would often see in electrochemistry. So one such jargon is polarization. Okay, so the difference between the equilibrium potential and the potential of operation of a cell, that's called polarization. And above the equilibrium potential, it acts as an electrolytic cell, and when you operate it as a galvanic cell, you get a potential that is less than that of an equilibrium potential. So how do you compute the equilibrium potential will be a topic which we will address in the next lecture. So going on, proceeding from what we covered in the last lecture, I would like to emphasize few things which you have to go back to your electrochemistry that either you studied, electrostatics that you either studied in your high school or in your first year of courses. Just go and refresh these concepts. So you should know the value of the elementary unit of charge of an electron, Coulomb's law, Coulomb's law of electrostatics. How do you think about dipoles, the definition, mathematical definition of dipoles? The most common dipole that you see in electrochemistry is that of water. What makes a water molecule a dipole, and associated properties like dielectric constant. You should have a good appreciation of these concepts. You should be able to draw the electric field strength around a positive charge and around a negative charge, why these arrows are directed in this manner. Okay, and what does it mean to have greater flux density, greater density of arrows? All these concepts you've been exposed to, but you should go and reinforce these concepts. There are two kinds of symmetry which you see in electrochemical system. One is spherical symmetry. You should be able to relate to the field strength of spherically symmetric systems. Why are we interested in this spherical symmetry? Because ions that are present in the electrolyte have spherical symmetry. You should be able to quantitatively discuss the field strength, suppose of systems that you commonly encountered in electrostatics. For example, if you have a point charge or a charge that is distributed over a sphere of radius r. Okay, so if you have such systems, you should be able to mathematically write down the field strength at any point r and why. What is the consequence of spherical symmetry? How does the field strength decay with respect to r? These kinds of issues you should be able to present these concepts in a mathematical, quantitative manner. The other symmetry which you would often see is this one. Okay, so in a parallel plate geometry, so this can be, the system which you've seen in your basic electrostatics classes is that you have an extended charge of uniform current density, positive current density, and negative current density. You should be able to mathematically write down the field strength inside and outside these systems. Why is this important in the context of electrochemistry? Because these extended charges are the model for electrodes, okay? The anode and cathode of the electrochemical cell. Okay, so you should be able to write and interpret the underlying mathematical equations. Okay, so go and refresh your electrostatics. That is the objective of this lecture. From field strength, you should be able to interpret the meaning of electric potential. Okay, so you should have a physical interpretation for field strength, and from there, using this notion of test charge. Okay, this is an abstraction in electrostatics. Okay, a unit test charge. This test charge is a fictional quantity. Okay, it's not really present in reality. You cannot see it in your laboratory, but this is a very useful fiction. Okay, it's a useful abstraction. Why do I call it a fiction? Because this has a point. This is a point charge. When you introduce this point charge, it doesn't really disturb anything else in the system. Okay, so so you think through this notion of test charge. Okay, and how do you go from field strength and test charge to electric potential? What is the physical significance of electric potential, its units, connection with work done, and energy? All these things you should go and refresh. You should be able to compute the electric potential changes. Let's say when a test charge goes from point A to point B, you should be able to clearly understand the meaning of a conservative field. Okay, and does it matter whether I go from point A to point B in this direction, or can I go in some other direction? Let's say you take a path from A to C to B. Is the electric potential difference between point A to point B, is this a path-dependent quantity or a path-independent quantity? And what is the meaning of a conservative field? Okay, so we should be able to clearly state what is, let's say, the work done when the test charge goes in this path from A to C. Okay, so we should be able to clearly analyze these systems in a mathematical manner. Okay, so all these things, again, I emphasize that you've seen this in your high school or first year of courses. Just go back and refresh these concepts. These are going to play a very important role in gaining intuition on electrochemical systems. So the potential difference in electrostatics is going to be very useful for analyzing an electrochemical system. The electrochemical system will comprise of two electrodes, and we'll often be discussing the potential difference between anode and cathode. In between an anode and cathode, you would have a complex dielectric. Okay, so this dielectric can get fairly complex. For example, you would hear as we progress in this class something called ionic liquids. Okay, so these play a very important role. For example, in batteries, you would hear a term called room temperature ionic liquid. This is, you should, I mean, as we progress, you will understand these things in a deeper manner. But what I want to emphasize right now is the chemical nature of these dipoles, which you would see dipoles and dielectrics and electrolytes that you are going to be discussing in electrochemical system has fairly complex chemical structures. So to interpret these complex systems, it's important you build some intuition using simple systems. What do I mean by a simple system? You go and look at the dipole of water and ask yourself the question, why is the dielectric constant of water so high? Okay, so how do I interpret that? What is the meaning of dielectric constant? Why is the dipole moment of dielectric constant of water so high? Okay, so you build some intuition, because such intuition built using simple system is going to help us build intuition on much more complex systems like ionic liquids and so on. Okay, so we would often be talking about potential difference in electrostatics. So as I mentioned in the previous lecture, the electrode is an electronic conductor. So the electronic conductor cannot support charges in the bulk of the system. Again, this is an idealization. Okay, so when we will be dealing with actually voltage drop inside the electrodes when we analyze the real system. But to begin with, it's good to have some simple notions from electrostatics. So in electrostatics class, you would have learned that if you have a charged metal, the metal is only on the surface. You should be able to interpret the physical reasons on why this is so. So in the bulk, there is electroneutrality. There is no net free charge in the bulk of the system. All the charge is only at the surface. So electroneutrality is absent only on the surface. You should be able to clearly understand the reasons behind such an argument. And then we would ask the question, what is the potential difference? How do you physically interpret the potential difference? Okay, so this can get quite complicated in an electrochemical system, but at least from the point of electrostatics, you should be able to understand the meaning of potential difference for this geometry, say, okay? And how does it vary with, let's say, charge density, distance between these two electronic conductors? How does it depend upon area of these plates and so on? Okay, so build intuition, that's the goal. Okay, in an electrochemical system, this interfacial structure between this electronic conductor and an ionic conductor can be quite complex. Associated with a complex interfacial structure, there is this potential jump. Okay, so right now I'm just mentioning that is a potential jump because corresponding to these charges that are present in the electronic conductor, there will be counter ions that are present in the ionic conductor side, on side of the electrolyte. Okay, so that itself has a complicated structure. It can decay exponentially, or it may have a lot of charges very close to this electrode. Okay, so we will discuss this in greater detail in subsequent lectures along this course. But what you should have some appreciation right now is there is a potential jump as you go from the electronic conductor to the ionic conductor. What is the magnitude of the potential jump? How do you well model these potential jump is a question we will address in this course. But right now there should be a potential jump. Have an appreciation for this potential jump. Okay, so this potential jump is associated with the interfacial structure. There can be counter ions present in this side of this is an electronic conductor. The counter ions present on the ionic conductor side give rise to this potential jump. Associated with this potential jump, there is current flow in the ionic conductor. Okay, so this is where things can get complex in electrochemical systems. Why so? Because the test charge associated with electrostatics. Okay, so whenever we talk about, let's say, electric potential, we discuss electric potential in utilizing an idealized test charge. Okay, this test charge, as I just mentioned, few minutes ago is a fiction, it's an abstraction, okay? It is not present in reality because the charges which we see in real systems are electrons, protons, and ions, okay? So protons and ions have a finite charge. You can also think about finite, not just finite charge, okay? It has a finite size, okay? So the test charge of electrostatics doesn't really have a finite size, okay? It is not, it cannot be represented in your experimental system that you use in your laboratory, okay? These are the real systems over which you take measurements. In these real systems, you really do not have a test charge. So the protons and ions which are present in electrochemical systems interact with the chemical environment. Okay, so the energy of the proton is crucially dependent upon the chemical environment. Okay, so when you introduce a proton into an electrolyte, it disturbs the chemical environment. The chemical environment responds to the introduction of a proton, the presence of the proton, and other ions. Okay, it can be cations and anions. All the cations, anions that are discussed in electrochemistry have some finite charge, finite size. How do you quantitatively discuss these issues? It's a deep question. We will address that to an extent, but at this point, I want you to be sensitive to only two issues. One is that the charges that we see in electrochemical systems, electrons, protons, and ions, have finite size and distinct structure, okay? So because of finite size and some structure, it does have some effect on the environment surrounding the protons and ions and electrons, okay? So an electron present in, let's say, copper is different from an electron that is present in gold, okay? So these are the matters of chemistry, okay? So while we talk about physical work using a test charge in electrostatics, the work that is addressed in electrochemical system is chemical work. What do I mean by that will be elaborated in subsequent subsequent lectures in this course. But right now, you should have an appreciation that the chemical environment, okay, plays a big role in defining the work involved in transfer of charges, movement of charges from one point to another. And these crucially depend upon how we think about the size and structure of these ions, okay? So some of these abstractions that you use in electrostatics have great utility, but great utility in electrochemistry. But when we try to translate these notions, there are additional complexities associated with the chemistry of the system. Okay, so we will introduce this very important notion of electrochemical potential to address these complexities. But right now, you just need to have an appreciation that there are these additional complexities that arise when you move from electrostatics to electrochemical systems. When you talk about currents in a simple electronic conductor, the way you're probably introduced to currents is via Ohm's law, right? When there is conventional current present in an electronic conductor, associated with the conventional flow of current is a potential drop. Okay, so this is the relationship between current and potential drop and resistance is given by by an empirical relationship called the Ohm's law. The basis can be derived from more molecular argument using statistical mechanics and even quantum mechanics. But in the first shot, it is just a useful empirical relationship. Okay, so you have this notion of on what does the resistance depend. Okay, the resistance decreases with area, increases with length of the conductor, and so on. You should be able to, you should revisit these notions, reinforce these concepts. In contrast to an electronic conductor, in electronic conductor, there's only one mobile charge, right, which is an electron, which is the electron. Okay, so electronic current it flows in the opposite direction as the conventional current. But in electrochemical systems, in the ionic conductor, there can be two kinds of mobile charges. There can be positively charged mobile charges and negatively charged mobile charges. They respond differently to the presence of a potential drop, and both of these, the flow of negative charges and the positive charges, contribute to the flow of current. Okay, so there is an additive contribution from the cathode as well as from the anodes. So again, the notions of electrostatics are useful in addressing electrochemical system, but additional concepts, additional complexity will be introduced when we discuss electrochemical systems. I'm addressing these complexities in a qualitative manner, but we'll make it more and more quantitative in the subsequent lectures. So if you want to use this kind of a representation for representing current flow in an ionic conductor, we have to necessarily introduce two kinds of charges. Both positive charges and negative charges contribute to current, and both of them add up to contribute to the net current. Okay, so we will make it quantitative in the next few lectures. So supposing we consider an electrochemical cell, but the potential imposed in an electrochemical cell is, let's say, insufficient to initiate reaction. Okay, so as soon as you impose the cell, you don't see an electrochemical reaction. You have to increase the potential beyond a particular quantity to see an electrochemical reaction. So let's consider a simple case where the potential imposed is insufficient to initiate a reaction. Okay, so what we would like to contrast here is the response of an insulator, electronic conductor, and an ionic conductor. When you impose a finite potential across an insulator, there can be some charge reorientation. So there can be some finite current and some charge transfer. But in a perfect insulator, after that, there is no longer a charge transfer, okay, with time. So that's a perfect insulator. Okay, there is, again, a perfect insulator is fictional quantity, but it's a useful approximation for analyzing many realistic systems that are used in experiments. Okay, so as opposed to an insulator, when a potential is imposed in electronic conductor, with time, the charge that is passed across the electronic conductor keeps increasing. And the increase in an ideal electronic conductor is in a linear manner. There is a linear variation of charge in an ideal electronic conductor given by I times T, right? In contrast to insulator and an ionic conductor, in contrast to an insulator and an electronic conductor, the ionic conductor behaves in a different manner. Let's understand how the ionic conductor behaves. So in this system, the potential is imposed on an electrochemical cell, but the potential is insufficient to initiate an electrochemical reaction. As soon as you impose a potential, the mobile ions that are present in an electrolyte gets transported close to the electrodes. Okay, so if there are positive charges present in the electrode, the negative charges get attracted to these positive charges. So these negative ions that are present in the electrolyte are the counter ions, okay, for these positive charges that are present in the electrode. Likewise, these mobile ions that are present in the electrolytes get attracted to the negative charges, okay. So because of the movement of cations and the anions in the electrolyte, there is finite current and finite transfer of charges. Again, this transfer of charges can be represented as I times T. Okay, so notice two things. One is the flow of positive ions in this direction will contribute to current flow in this direction. Flow of negative ions in this direction will again contribute to current flow in this direction. Okay, and there is a continuity of electric current across the circuit, right? This is something which you've seen in your basic course in electrical engineering. So you should, this is the direction of conventional current. So there's a continuity of electrical current in an electrical circuit. So such notions are also applicable when you go from just an electrical circuit to current inside a electrochemical cell. So when you impose such a potential, if you see the current decays with time, at infinite time, as the time progresses, at infinite time, this current becomes zero, and the amount of charge that is transferred with time also becomes zero. Why? Because all these ions have oriented themselves with respect to the free charges that are present in the electrode. Okay, so it is not that all the ions that are present will just accumulate here. That's not the ideal, that's not the real structure of the interface. There will be an exponential decay. We will address why there is an exponential decay using what is called the Debye-Huckel theory. This Debye-Huckel theory provides us with a quantitative way of representing the structure of what is called the double layer. Okay, why do you call it a double layer? This is the first layer, and the structure in the electrolyte, because of there is structure that is present because of the presence of mobile ions, provides us with the second layer. Put together, they are called the double layer. Okay, the Debye-Huckel theory provides us with a quantitative method for describing the structure of a double layer. Again, we'll introduce this in the subsequent lectures. Okay, so what you should have an appreciation at this level is the contrasting behavior of a perfect insulator, a perfect electronic conductor, and a ionic conductor. Okay, so when a potential is being imposed on these three different systems. So in this simple system, what do I mean by what makes this system simple? Okay, this potential that is applied doesn't initiate an electrochemical reaction. That's what makes this system, this electrochemical system, simpler compared to the electrochemical systems that we will be looking at in subsequent lectures. But even in the simple systems, it's useful to relate your notions of Ohm's law, right? So here, let's say you have a potential drop in the ionic conductor in the electrolyte. In response to this potential gradient, there is flow of current. Both anions and cations contribute to the flow of current. Notice the direction and magnitude of the potential drop. Okay, the potential drop, if the potential gradient is in this direction, the current that is flowing is proportional to the potential gradient, and this proportionality constant is represented in this manner using these notions of conductivity and so on. Again, all these notions come from electrostatics, but the actual situation is more complex because of the presence of two mobile charges, right? Anions and cations. But again, these notions from electrostatics carry over to electrochemical systems. So overall, we can have some notion of Ohm's law even for the ionic conductor, even though there are Ohm's law was introduced only because of mobile electrons in an ideal electronic conductor. In an ionic conductor, even though there are anions and cations, this notion of V is equal to IR, okay, is still present. Okay, so this notion of conductance, conductivity, resistance, all these can be translated from electrostatics to an electrochemical system. We'll move on from electrostatics and electrostatic notions relevant to electrochemical system to the first quantitative description of an electrochemical system made possible by Michael Faraday. He tabulated these laws in the years 1833, 1834. This is actually a bookkeeping procedure. Okay, there's nothing more than bookkeeping procedure. What do I mean by that? Okay, so there are notions of thermodynamics, transport phenomena, electrochemical kinetics. Okay, so none of these notions are utilized in tabulating Faraday's law. It is just notion of mass balance and charge balance that is being utilized to formulate the two laws of electrolysis, which you've been introduced in your high school itself. Okay, so what is the system that is being discussed? You have, let's say, zinc salt in the electrolyte, and you impose a potential, a cathodic potential. A cathodic potential will introduce reduction, cathodic reduction of the ions that are present in the electrolyte. These ions will combine with the electrons in the electrode to electrodeposit zinc metal. Okay, that is the electrochemical system we are discussing. Okay, so of course these are relevant to wide range of electrochemical system, but I'm using this as an example. What is the first law? The mass of the metal that is being electrodeposited, in this case zinc, is proportional to charge passed in an electrochemical cell. Okay, it is almost self-evident, but Faraday played the important role of documenting the mass of material that is being deposited. So till then, this quantitative description was not attempted. Okay, so Humphrey Davy and Volta Galvani, they all did important electrochemical experiments. Okay, these are very interesting. In those times, just imagine, in late 1700s and 1800s, even the notions of atoms and electrons were not accepted. Okay, till even late 1800s. Okay, these things were not accepted. So they did these experiments in times where none of these notions were present. Okay, so these are just great experiments, great insights. But this seemingly trivial law is important because Michael Faraday paved for a quantitative description of electrochemical systems. Okay, so that is the first law. The second law helps us take into account few other features of a chemical system. What are the features? Different elements have different valency. Again, this is a concept that been introduced in high school. You should know how to think about these concepts. Again, this is a useful notion. Okay, does a real cation have two positive charge? These are deep questions. Okay, which can only be answered by appealing to quantum mechanical theories. Okay, so what exactly is the meaning of these two charges that we are introduced from inorganic chemistry from your high school? Okay, what exactly is the meaning? Okay, so that's a deep question, but at a simple level, we have this notion that different ions have different effective charges associated with them. Okay, for example, when you talk about alkali metals, you are talking about monovalent cations. Okay, when you talk about lithium, sodium, potassium, rubidium, cesium. Okay, so these are all elements, alkali metals. When you have alkali metals, you have a single positive charge associated with them. Then when you go to beryllium, magnesium, calcium, the alkali earth metal, these are divalent cations. Okay, we associate two positive charges. So, and then let's say when you go to aluminum, chromium, you have three positive charges. Then you go to, let's say, titanium, hafnium, zirconium, you will have tetravalent cations, right? Likewise, you can have anions of different charges, right? So the second law of Faraday is useful for discussing how much of material is being deposited when current is passed through the electrochemical interface, normalized to the molecular weight of the material and the charge required for reducing the ions in the system. Okay, so this is probably a lot of words. Let us make it more quantitative. Okay, make it more simple. So we have this notion of equivalent, okay, chemical equivalent, okay. This is a notion which you have probably heard in your high school chemistry class. This is associated with mole of charge, okay. So here, to reduce 1 mole of zinc 2 plus, you have to pass 2 moles of current, okay. So likewise, if you want to reduce, let's say, aluminum, okay, which was an important electrochemical process demonstrated in 1800s, you need 3 moles of charges to reduce 1 mole of Al3 plus to get 1 mole of Al. Okay, so here you need to pass 2 moles of charges to get 1 mole of zinc present. 1 mole of charge is called Faraday constant. You should know the magnitude of Faraday's constant. So you get the magnitude of Faraday's constant. This is the magnitude in the unit is Coulomb per equivalent. You get that by elementary unit of charge times the Avogadro number, right? So you should know the magnitude of each of this quantity that has been introduced in from high school. Okay, so what is the second law can be made clear. The second law of electrolysis can be made clear by a typical representation that is utilized for representing a half cell reaction. Again, this is a jargon. What do you mean by half cell? An electrochemical cell, a complete electrochemical cell, has a minimum of 2 half cells, okay? The anode and a cathode. In the half cell reactions can be represented independent of each other, okay? There is a cathodic reaction and an anodic reaction. Put together is the overall reaction that is occurring in electrochemical cell. However, the reactions that are occurring in a half cell can be represented in the following manner, okay? So here I represents a species, chemical species can be, for example, in this case, zinc 2 plus. Si represents a stoichiometric coefficient for that particular chemical species. For example, the stoichiometric coefficient for Zn2 plus is 1 in this case, okay? And for this system, N is 2, okay? The number of electrons involved in this half cell, okay? So that is a way of representing a half cell reaction. What is the second law of electrolysis? The mass of material that is deposited, okay, or consumed, okay? So we can, if you're thinking about hydrogen evolution reaction or oxygen evolution reaction, we will talk about these things in the course, okay? We can also use Faraday's laws of electrolysis. In the simplest case, it's useful to think about mass deposited, electrode deposited, okay? There are some ions of different charges, different valencies, and you are cathodically reducing these ions and depositing the metal on the cathode, okay? So the mass that is deposited is dependent upon variety of factors, okay? It is dependent upon the molar mass, that is the molecular weight of the material, gram per mole, that is the unit. Of course, it depends upon the charge. It does depend upon the stoichiometric coefficient, in this case 1. What is crucial is that for different materials, different amount of charges are required for getting just 1 mole of material. Okay, in this case, 2 moles of charge is required for depositing 1 mole of zinc. Okay, so all these things are incorporated and has to be taken into account for renormalizing this charge. Okay, so this 2 here comes here, N here. So, and then all these things are brought together in this more or less self-evident mathematical formula. Okay, so this is the charge on a mole of species, mole of electrons in this case, and this will give you the mass that is deposited, taking into account the stoichiometric coefficient present in the electrochemical half cell reaction, the number of electrons that are required to deposit just 1 mole of a material. Okay, so this is mathematical equation is almost self-evident if you think about this, but it is still very important because this paved way to mathematical and a quantitative treatment of electrochemical system. That's why Michael Faraday is often considered to be father of electrochemistry, okay? Because even though there were a lot of interesting electrochemical observation prior to Faraday, Faraday documented some simple equations. Okay, these simple equations are fairly simple, but still they are mathematical equations that helped represent electrochemical systems in a quantitative manner. With this, we will go towards more quantitative analysis using thermodynamic principles. So that is the subject matter for the next lecture. Thank you.